All right. So let's take a look at the Lewis structure for this. Lewis structure, we want to put the bonds in the plane like this. So did you guys do this?
No.
Yep.
And then, what about the lone pairs? How did you treat the lone pairs?
Stick out, stick in.
Stick out and stick in. So you have to show it differently. There. And so we have a tetrahedral arrangement of electrons. However, the geometry, the shape of the molecule is bent. And the angle?
104.
Yeah, around 105. You know, it's less than 109. I just say around, because if we start trying to be too precise, then you know, with these angles, there's slight distortions and that kind of stuff. So we don't want to get too precise, saying it's definitely going to be 104.5. It could be off a little. Am I recording this? Yes. All right. Next thing we got to do is we got to figure out what's happening with the valence electrons. How many valence electrons does nitrogen normally have? And so it's got these two core electrons in the 1s, and then the 2s and the 2p. It normally has 5 valence electrons, but that's for a nitrogen with a 0 formal charge. Is this nitrogen? Does this nitrogen have a 0 formal charge? No. What is the formal charge on this nitrogen? Yeah. It's minus. And therefore, that means this nitrogen will have 6 valence electrons. And so we'll fill these 1, 2, 3, 4, 5, 6. We got a pair. So this gives us 2 pairs, 2 lone pairs, and 2 singly occupied. And then the hydrogens can come in and bond here and bond here. 2 hydrogens come in. But you might have thought that there's something odd about this. You know, is there something weird about this? Has to do with the angles. There's just something weird about the angle. What did we say the angle is? 109. Less than 109? So the angle is less than 109, which maybe about 105. And so what is weird about the angles? That's my question. What is weird about the angle? If anything. Maybe nothing's weird about it, but think about it for a minute or two.
Why would it be weird?
Should be.
Well, nothing's weird about the angle. I mean, it's what you predict, 105 degrees, right? Or something, 109. Less than 109, you could just say that. Maybe nothing's weird about it? You don't think nothing, everything looks okay?
Yes.
All right, so this is our little peek, and actually it's not a little peek. This is why I say I'm combining chapter 12. In chapter 12, we're looking at bonds and how bonds form. And so basically we use 2 bond theories. And so we're going to be talking about something called valence bond theory. and something called molecular orbital theory. Well, valence bond theory is very simple. A bond equals the overlap of two atomic orbitals. So if I have a hydrogen here, 1s, hydrogen, 1 electron here, and then I have another hydrogen, 1s, with 1 electron here, what's going to happen is they're going to come together and form a bond. And when they come together and form a bond, we just overlap the two 1s orbitals. We've got to flip one of the electrons, like this. But this would be H2. H2 consists of what we call a 1s bond, or 1s sigma bond. And so this is called a 1s sigma bond. It's a sigma bond because of the overlap occurs in the internuclear axis. That's what sigma refers to.
What's those little dots?
These dots
No.
connect the
Is that the dot like the nucleus?
the dots are the nucleus. Internuclear axis. So it's very simple. You take an s orbital and s orbital, overlap them. What happens when you overlap them? What happens to the electron cloud?
It's more dense.
Yeah, the electron cloud in the overlapping region becomes more dense. And so when we look at the electron cloud, yeah, the electron cloud becomes more dense here, and becoming more dense here means that the nuclei are going to be held right or tightly. And so this is the bond according to valence. And again, we call this a 1s because it's a 1s orbital, another 1s orbital overlapping in the internuclear axis, sigma bond. 1s sigma bond. Any problems with that? No. So let's do something a little bit more complicated.
So is there anything weird about the end?
Maybe not. What about the angle?
Anything weird? Like,
Maybe.
wait, I'm lost.
Okay, what are the orbitals, the valence orbitals on nitrogen?
2p.
It's a 2p. Okay, so here's a 2p orbital, right? And it has 1 electron. And then this 2p orbital is going to bond to a hydrogen. The hydrogen's small, so let's draw a little circle like this. This is my hydrogen. There's 1 electron here. And so this is the electron I labeled in green here. And this is the one in black here. And so do you see this 2p orbital here has 1 electron, and this hydrogen comes in and bonds with it, and we're going to get overlap of electron clouds here, which is going to make the bond. It's going to have a higher dot density. No problem with that? No. Where does the other hydrogen come in? To what other orbital does it attach to? Well, actually, while thinking about that, this is called a 1s2p sigma bond. It's a 1s2p sigma bond because we're overlapping a 1s orbital with a 2p orbital. And if we look at the internuclear axis, we just draw a line through the nuclei. The overlap occurs within that internuclear axis. Where does the other bond come in? Where does the other hydrogen come in? What orbital? What does it attach to? Another 2p. How many 2p orbitals do we have in total? 3. And so the other 2p, let's draw it along this axis. I'm going to draw the line a little differently to differentiate it. And so here's our next 2p. 2p orbitals have these 2 lobes. And so our other 2p has 1 electron here. And then the hydrogen comes in and bonds to it here. So what kind of bond is this? Yeah, it's going to be a 1s 2p sigma bond. Okay, now, do you see something funny about the angle or no? This angle should be 90 degrees because the p orbitals, you have one on the z, one on the x, and one on the y. The x, y, z axes are 90, orthogonal. And so the bond angle is supposed to be 90 degrees. And then you have another 2p orbital. The other 2p orbital, sits out here. Let's make the outline different. One lobe pops out, the other lobe pops in. This 2p orbital has a pair of electrons. And then you have the 2s orbital. The 2s orbital has a pair of electrons. This is the 2s. But this 2p orbital here and this 2s orbital here are filled, so no hydrogens can attach. The only place hydrogen can attach is this p orbital here along the x and this p orbital here along the y. Do you see that? And if this is x and this is y, then the bond angle should be 90, not 109. So where are we getting 109? What orbitals have a 109 angle? The d orbitals? No, the d orbital is 90. Yeah, what happens is repulsions take over. And we could see the repulsions here if we go back to ammonium ion. When we look at ammonium ion here, remember we said that this is isotropic, it's symmetric, right? There's no difference between these bonds. And so if you put 3 of them at 90 degree angles and then stick, 3 of them at 90 degree angles and then stick a fourth somewhere here on the sphere, the hydrogen can attach anywhere on the sphere, what's going to happen is there are going to be repulsions. And so what happens is something called hybridization. Have you guys heard of hybridization before? Never? Okay. Because of the repulsions, the orbitals hybridize to minimize the repulsions. Excuse me. So let's talk about hybrid atomic orbitals next.
What is meant by hybridized?
What do I mean by hybridized?
They get together and fuse.
Hybridized. Remember what was hybrid? Remember hybrid? We saw that before. A mixture. Yeah. Sorry, this is chapter 11. If I look at, we're going to talk about two things. We're going to talk about maximizing bonding and hybridization. If I look at carbon, carbon has 4 valence electrons. Carbon technically should only form 2 bonds. Do you see it? Yeah. But it can form actually 4 if I pop this electron over here and I get 4 singles. And then it can form 4. But when I do that, then the repulsions kind of get big. So let's take a look at. So this is what we call an excited state. We pop this electron over here. Now we can maximize bonding. So this is hybridization. What we do is we take S and a P and a P and a P, and then we mix them together. But we don't get one orbital, we get 4 new orbitals. Each new orbital here consists of 1/4 S and 3/4 P. And so 1/4 S, 3/4 P, we'll just call it 1 part S, 3 parts P, or an sp3 orbital. And it turns out these 4 new orbitals are equivalent. Versus, you know, the S and the 3 P's that we started with are different, the S being different from the P's. These 4 new orbitals are equivalent. And so this is an sp3 orbital. Usually we don't show this lobe. We only show one lobe of it, the blue one. And this, and this, and this. Minor lobe. And so this is the representation in a set. When you look at this, what shape is this? Tetrahedral. And so tetrahedral means we must be using sp3 hybridized orbitals. And so here's how we can get the 109 angles from this. And this is what happens here in methane. So let's take a look at methane. There are 2 steps that are happening here. One, we're promoting an electron, and then 2, we're hybridizing. And so what we have is we have these 2 subshells, and we're going to mix these to create one subshell, the sp3 subshell. And this is the 2 sp3 we want to keep in. And each of these is called an sp3 orbital. So this would be an sp3, this is an sp3, this is an sp3. 1 part S, 3 parts P. This is an sp3. And so, in other words, we make new atomic orbitals. Here are our old atomic orbitals. These are our new atomic orbitals. This costs energy to make these, but the return is we minimize repulsions. Rather than having a 90-degree repulsion, we end up with a 109 repulsion. And so it turns out to be energetically favorable to do this. And so this is a quantum mechanical mixing of the wave functions to generate new wave functions. Does that make sense? So there's wave mixers. Create new waves. Well, what happens now is, okay, this is carbon, and then we have our 4 hydrogens come in like this. Boom, 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 here. The angles, 109.5.
So there's nothing wrong with the angle that you show for the MI?
No,
There's nothing wrong with it.
no.
It look weird because it's supposed to be 90, but
Yeah, it's supposed to be 90, but if
But
you know
the
hybrid orbitals,
hybrid orbitals make it 1.
yeah, it makes it 109. And so, how do you know? Well, there are different types of hybridization. And so, what we're going to do is sp3 is the most common one you'll encounter. So let's spend some time talking about sp3 hybridization and how you can draw it. And so this is the way I do it here. For carbon, I'd show it like this. And then the hydrogens come in here. Actually, I should do this earlier. We have a hydrogen 1s bond, hydrogen 1s, and then bonds, hydrogen 1s, bonds here, hydrogen 1s, bonds here. Okay. All right, now I want to be able to do a couple of drawings. One, I want to do a 3D Lewis structure. 3D Lewis structure for methane looks like this. Like this, right? This is the 3D Lewis structure for methane. Okay, now I'm going to kick it up one more notch, and we're going to do a 3D valence bond drawing of this. So let's do a 3D valence bond drawing. And so when we do a 3D valence bond drawing, then we need to know how to draw the hybrid orbitals like this. And so this is an sp3 orbital here and here. We draw two sp3 orbitals in the plane. And that means one sp3 orbital sticks out like this, and the other sp3 orbital sticks in. This is sp3, this is sp3. That gives us our four sp3 orbitals. Each of these sp3 orbitals has a single electron, because this is carbon with a zero formal charge. This is a neutral carbon with four valence electrons. Okay, then we're going to have the hydrogens come in. Here. This is an S. Sometimes you can drop the N designation. If we drop the N designation, we call this an sp3 orbital. Sometimes we like to leave the N designation, because what do you think is stronger bond? A 1s to a 2 sp3, or a 1s to, let's say, a 5 sp3? Yeah, like a 2 sp3 is this big, a 3 sp3 is this big, a 4 sp3 is, it just grows bigger, just like a 4s, a 5s, a 6s. And so what kind of bond is this? This is called an sp3 sigma bond. Got that here. This one is a sp3 sigma, sp3 sigma, and sp3 sigma. And so here we show the bonds in the valence bond drawing, and we show the bonding in the, what's this called, this diagram? Energy, orbital energy level diagram. What's happening with the 1s? Nothing's happening with the 1s. The 1s stays as is. It's just the 2s and the 2p valence orbitals that get hybridized. And so the 1s is still there as the core.
How come you don't label it like 2 sp3?
They should. We should. It should be called, this is a 2 sp3, a 2 sp3, a 2 sp3, a 2 sp3. So we have 4 of those. But when you're doing this, it becomes more of a hassle. You know, it gets too busy. So we'll do it like this. Can you do this for me for ammonium, NH4 plus, and amide? Can you try that? Try to draw those. Ammonium and amide. Actually, you know what? I want you to do 3. I want you to do ammonium, ammonia, and amide. Orbital energy level diagram. Except now our orbital energy level diagram, we want to hybridize. And we're going to draw the, what did I call this drawing? The valence bond drawing for this. Do that, and then let me see it.
What's it called again?
Valence bond. Valence bond analysis, valence bond drawing, whatever you want to call it.